Jessica, and Jessica is going to tell us about replicability in learning. So, thank you.
Thank you very much for the introduction. Thanks for the amazing workshop. Thanks to all the organizers. Yeah, so today I'm going to be talking about joint work with a bunch of people, several of whom are in the audience. So this is going to be work with Mark Bunn, Marco Gavardi, Max Hopkins, who's a grad student at UCSD, Russell, Rex, also a grad student, Tony, and Sachet, who's a grad student at BU. So before we get into our definition, I sort of just want to talk informally about what we're going to mean by replicability and why it's important. So this is, ideally what the scientific method looks like, right? So in our little caricature here, we have a scientist. Here it's Dr. McNibbles. And Dr. McNibbles has some hypothesis that they want to test, right? So they have some hypothesis that like drug A is going to be an effective treatment for disease B. And so what are they going to do? They're going to design an experiment to collect data. And then they're going to perform some sort of hypothesis testing analysis on that data, conclude whether or not drug A is in fact an effective treatment for disease B, and then they're going to report that to the broader scientific community. So if what we're really doing when we perform these experiments and these analyses is capturing an enduring real world phenomena, then it should be the case that another team of scientists could come along, follow Dr. McNibbles's experimental procedure, collect their own data, perform the same analysis, and obtain the same results, right? That's ideally what we'd like to have happen. And that's what we're going to mean when we talk about replicability. But as many of you may know, the real world looks very different from this idealized picture from the previous slide. So there's this survey, real quick, just to give you an idea of how dismal the situation is. There's a survey published in Nature in 2016 by Baker, just surveying scientists from a variety of fields about failures of replication, right? So I feel like the social sciences in particular get a bad rap for failures of replication. But this survey was for what we might call like the hard sciences. So don't know if you can see it, but they surveyed chemists, biologists, folks in physics and engineering, medicine, earth and environmental sciences, and then others. And the red bars here are scientists who had failed to replicate somebody or reproduce somebody else's results. And you can see that well over 50% in most disciplines had failed to reproduce a finding. And then this lighter pink bar here is how many had failed to reproduce their own findings, right? And that's not great. And if this is just one survey, maybe you don't trust one particular survey so much, but if you go to the Wikipedia page on the replication crisis, you can have a very bad afternoon if that's your idea of a good time. Yes.
Actually, the question is like, did you ever actually fail to replicate like single experiment?
Yeah. So it's sort of maybe not super compelling because you're imagining people might be performing many experiments. Is that the point? Yeah. So they're asking, have you failed? Yeah. So the question was, have you ever, is this saying anything about like the fraction of experiments that you failed to replicate? No, the survey was just asking, have you ever, like once, failed to reproduce itself? Okay. So in our work, we're going to, or actually in previous work with Russell, Rex, Tony, we tried to introduce a definition to capture algorithms that replicate. And what we're going to mean by that is a randomized algorithm A will be row replicable if it's the case that, notably for any distribution D, over some domain X, if we draw two samples from this distribution and run the algorithm twice, one on each sample, and hold the randomness fixed between both runs, we should get exactly the same output, except with probability row. So this is going to be like the notion we're going to be discussing. We'll discuss a number of other stability notions, but this is maybe one of the more novel ones we'll be discussing over the course of this talk. So if there are questions, yeah.
What's M?
And here, so we're going to imagine that the algorithm A takes a sample from a distribution that will be of some size. And so you can imagine if you have a learning algorithm, M might vary depending on your target accuracy parameters and things like this.
So like S1 and S2 are vectors of samples or something?
Yeah,
They're
yeah.
like vectors of things.
Yeah, we're drawing like multiple
Oh, I
times
got it.
IID from
I got it,
the
okay.
distribution. Great question. Yeah.
So this is not assumed to be a decision.
Okay.
This is not assumed to be a decision algorithm.
Is not assumed to be a decision algorithm. I think that in the case that A is a decision algorithm, this particular definition is particularly well motivated. To maybe anticipate questions that I have gotten a lot about this work is, why do we have this strong requirement that we're getting exactly the same output, right? It's like, what if we just get two good outputs? And in the case, especially if you have a decision problem, well, what does it mean for two outputs to be close? It's going to be 0 or 1. So we only get exactly the same decision. But we're not assuming this. Other questions about, yeah.
So for the R being the same in both, like this is, you choose a random R and you feed the exact same one each time to both of them?
Yes.
Okay.
Yep.
Is this like a weakening of pseudo-determinism?
Okay, great. Thanks.
Oh.
So it is inspired by work on pseudo-determinism. I'll maybe point out some differences between this definition and pseudo-determinism. Yeah. Work on pseudo-deterministic algorithms look here. In the case of pseudo-determinism, what we want is it for to be the case that for all inputs, most random strings will yield the same output. But notably, what we're re-randomizing in that case is coming from a fixed distribution, right? The uniform distribution over random strings. Here, what we're re-randomizing is coming from a arbitrarily behaved distribution. So we have to work for all distributions. So that's one significant difference. Another is the quantification over the input, right? So this is going to be average case over, yeah. Okay, yes, but it is inspired very much by the definition of pseudo-deterministic algorithms. Yes.
In some sense, it's a dual notion. In pseudo-determinism, you want the output to depend on the input, but not the randomness. Here we're saying we want the output to depend on the randomness, but not the input.
So should I think of M as being a function or is like?
You should generally think, so A, typically, I guess in the learning setting, we'll have an algorithm that works for, I think you can like a sort of family of functions where we'll have target parameters, maybe for replicability, maybe also for accuracy. Those will fix M and then but we will show, I guess in a second, how the replicability parameter rho is going to affect the Great. Okay, so as a brief aside, also because Igor brought this up, and so in case anyone saw the, saw previous talks or saw this paper in Stock 2021, there has been a rebranding. So this is replicability, previously known as reproducibility. So I just want to call that out real quick in case anyone's confused. The ACM put out some guidance clarifying distinctions between replicability and reproducibility, where replicability is fixed to say that a team of scientists can collect their own data and obtain the same results, whereas reproducibility means that you use the same data that the previous team used and can obtain the same results. And so because we're resampling our input data, we thought our notion was more aligned with replicability and we didn't want to fight the ACM. So we decided we just confuse people instead and change the name. So I just wanted to head that off. Okay, great. So we were inspired by this work on pseudo-deterministic algorithms, but there was actually at the same time a team at Google, Ghazi Kumar and Manarangsi, introduced essentially equivalent notion called pseudo-global stability. They used this in their work on user-level privacy, and they pseudo-global stability, as they define it's a little bit different, that they have two parameters. They sort of separate out rho into failure probability over random strings and failure probability over the sample. And this in turn was a generalization of global stability, which was introduced by Bonlevny and Moran in their work characterizing private pack learnability by Little Stone dimension. So today I'm going to talk about connections between replicability and other important notions or stability notions in learning and statistical analysis. So we're going to talk about replicability, how it relates to differential privacy, how it relates to max information, and how it relates to one-way perfect generalization. That's all for today. But first, I want us to get a sort of flavor of replicable algorithms to sort of see like how they work. There's sort of maybe one weird trick that at a high level underlies most of our algorithmic results. And so I want to show you this trick so you can sort of have that in the back of your head if you're wondering how do we get replicable algorithms in practice. Then we'll talk about the connections. We'll define all these relevant notions I just showed on the previous slide. We'll discuss a few applications and then actually, talk about how we're going to prove or how we're going to draw some of these arrows in the diagram. Let's get into it by showing how we can make reproducible statistical, or how we can simulate a reproducible statistical query oracle. For those who aren't familiar, this statistical query model was introduced by Kearns to capture the problem of pack learning under random classification noise. And the idea here, as opposed to like the standard pack learning paradigm where your learner gets access to labeled examples, here the learner is only going to get access to statistical information about the underlying distribution. Okay, so the learner is going to have some sort of query, they'll submit it to the Oracle, and then the Oracle will give them something that is close to the expectation of that query over the target distribution up to some additive tolerance parameter tau. And in practice, we can implement a statistical query oracle using a large enough sample, right? So we have these queries that concentrate. If we have an IID sample, then we can use concentration bounds to say, that, okay, I can hit whatever additive tolerance I want by just taking my sample to be large enough. This won't work for us in the case of replicability, right? Because we're in this previous non-replicable statistical query oracle setting, we're using a sample to empirically compute the quantity that we want to return, right? So our answer is going to very much depend on the sample. So, say the expectation of the query is really this green dot here, and we're going to draw some sample and return A1 based on the sample S1 that we drew. Well, maybe it's an underestimate for this particular sample, but we draw another sample and we get an overestimate, right? Clearly the blue dot is not the same as the green dot, and so we will not be replicable. There's in fact this 2 tau interval in which our empirical estimates could fall. So what are we going to do about this? We're going to start by partitioning the range, the 0-1 interval, into subintervals of width alpha. Okay. And now we're going to define canonical representatives of this partition. So we'll take the midpoints of each subinterval. And now when we compute our empirical estimate, rather than returning the estimate itself, we're just going to return the canonical representative from the interval that we fell in. Okay. So now in this pretty picture here, hey, like our 2 empirical estimates are in the same interval, we return the same midpoint, and we're replicable, great. But we're not done yet, right? This is a sort of nice case where the expectation landed in the middle of an interval. But what if it actually fell on the boundary or close to a boundary between 2 intervals? Then some samples will land in this region, some will put us over here. And again, we won't be replicable. But we haven't used our random string yet, right? So we haven't actually used randomness. So what we're going to do is we're going to choose the first place that we draw a boundary using our random string. We're going to pick some value from in between 0 and alpha, draw the first boundary there, and that will and then draw every subsequent boundary after with alpha, and that will let us randomize where these boundaries fall. Okay, so some choices of boundaries will be good for replicability, some will be bad, but we can now bound the probability that we picked a bad starting place as follows, right? So there's this 2 tau region that we want to avoid with a choice of boundary. We're choosing the boundary from a range 0 alpha, and so we can by choosing appropriate parameters, we can hit whatever target replicability parameter you like. Yeah. I'm sorry?
You just apply the parity sensitive hash function to the output.
Do you know, Russell? I don't.
I think so first, we want to look, you can think of this as a kind of local sensitive hash function, okay? But where so the problem with just using a vanilla LSH is that the value you hash to might not be associated with any kind of interval. And so we want to actually like have an LSH that's actually mapping you to a point that's nearby.
So you really want the domain in the range to be the same.
Yeah. So, but you can think of this as one particular construction of LSH with that additional property.
Great question. Any other questions?
We're going to trade-off here between replicability and tolerance.
Yeah, so do you mean, or maybe I'll go on to what I was going to say next and you can see if that answers your question, which is that because we are rounding to sort of the canonical representative for our interval, that we can only actually have accuracy order alpha, right? Is that what you're getting at here? Yeah, okay. Right, so in this case, yeah, our tolerance parameter is going to be fixed by this alpha parameter. And the idea here is that, okay, if we have a particular target accuracy, we'll pick alpha to be that. And then we have a target replicability parameter, and that's going to be this 2 tau over alpha, right? Where tau is sort of the tolerance of the non-replicable statistical query oracle that we're simulating. And so we'll need a larger sample, right? And in order to balance these parameters, but they'll be polynomial, and we'll end up with an inverse quadratic dependence on replicability and the sample complexity. Other like the 1 over tau squared that you would expect from just doing the empirical estimate.
Maybe you'll get to this in a sec, but like in the idea of like application, I guess, to a science experiment is you would use this mechanism and then you publish the random seed and someone else is supposed to exactly copy that, or okay.
Exactly. So if somebody wants to obtain your results, and you would publish the randomness that you used, and then they know that if they go out and use that same randomness for their own sample, they should obtain the same.
So this is for like single query.
This is for a single query. So replicability will compose for adaptive queries though, and so you can use this to run your favorite statistical query algorithm. Yeah.
Does that include like hyperparameter tuning? So to his question, like if I search a grid of, have you thought through this specific example? I'm searching a grid of hyperparameters with a canonical representation of each hyperparameter. Now maybe I could make training like large scale models more replicable, not reducible now if I publish the randomness that went into that.
Interesting. So okay, so what you're proposing is, I guess like at a high level, like if you can model each step of the analysis process by a replicable procedure, then yes, by composition, you should be able to say that that the composition of all of these choices will also be replicable. I'm not sure exactly. I don't think I have a clear enough picture of the flow of hyperparameter tuning in my head to actually be able to say, but yes, I think if you can model each step as a replicable procedure, then you should be good. Okay, yeah.
Is there any interpretation that makes sense of like maybe the case where you want to redo some of the randomness, like maybe keep the first half of the random points constant? It's partially randomized.
Yeah. So you're imagining that. So I think at this point you can sort of treat those coins as like maybe part of the sample as well. So we're just imagining the public randomness is going into this second parameter, and then you're resampling the rest. And so I think that.
What if you only publish part of the randomness?
Well, maybe I'm misunderstanding the question, but since we're resampling everything else, right? We're resampling from the underlying sample, but then you're also sampling from the same distribution over randomness, right? And so you can. I guess like it,
You can like fold it into the D, right?
yeah, this is what I'm
Yeah,
saying,
yeah,
yeah. And I should also, oh, sorry.
Yeah, so we showed that for replicability in itself, releasing all the randomness is the optimal thing to do. But for efficiency and communication, there might be a reason to reduce the amount of randomness. We haven't really investigated that. That was actually in the Grossman-Liu paper on pseudodeterminism for small space computation. That was kind of their main point, is to minimize the amount of randomness you release.
I guess I'll maybe piggyback on that, just observe that I believe it's also the case that if you sort of relax this worst case distributional assumption and start introducing smoothness properties, you can also reduce the amount of randomness required. So this sort of trick that we did here, right? Like the thing I called the one weird trick is that we used our randomness to pick a random discretization of the output space. And then we snapped our empirical estimates onto that grid. And so if you have like maybe smoothness, then maybe you can take a wider grid. And so you don't need as much randomness actually.
So in the Grossman and Liu paper, they get sort of logarithmic accuracy parameters actually. Is that also what you get here?
So we don't have any. So okay, I guess like your number of bits of randomness is going to be fixed by the representation size of alpha, and so yes. Great. So there's a lot to talk about. So any other questions about the definition? I would love to hear them from you, but probably offline. I also point out that this is essentially tight sample complexity. So we also have complexity matching lower bounds, showing that this inverse quadratic dependence on rows is necessary. Okay, so back to other notions of stability and drawing all the arrows in this diagram. So first I want to actually, tell you what all of these definitions mean so we can see why we think they may or may not be related. So let's start with epsilon delta differential privacy. Okay, so the idea with differential privacy is we want to limit the amount of information that our analysis is going to leak about individuals in our data set. Okay, so in this case, we're going to be worst case over data sets. So it's not like an average case assumption here. We're saying you're differentially private if for all neighboring data sets, where neighboring means we've swapped out an individual. In this little sketch here, we can imagine two neighboring data sets. This one has a bunch of people. In particular, it has Marco Carmesino here. And then in S prime, we have swapped out Marco for Mark Button, just picking on two people in the audience. But otherwise, the data sets are the same. Okay, this was introduced by Dwarf and Sharing. It should be the case that if we run our analysis on these neighboring data sets, that the distributions over outputs that we get are close. Okay. So any questions about privacy?
So in particular, in this example, it doesn't matter at all that some string distance between names is very small. I mean, I just very adversarial examples. This is kind of a special case, isn't it?
Great, fair observation. Fair observation. Okay, so moving on to max information. So this is introduced by Dirk Feldman, Harper Tassi, Marco Roth. We work on stability under adaptive data analysis. And we're no longer going to be worst case here. We're not going to care so much about individuals as we care about samples. So max information is going to informally bound how much you can learn about the sample from looking at the output of the algorithm run on that sample, right? So the idea is if you're not leaking too much information in your output about the specific sample, then the joint distribution over samples and outputs of your algorithm on that sample should be sort of close to the product distribution between the samples and algorithm run on samples drawn from D. Okay. So, we need to leak some information about the sample because we're trying to learn something about the distribution from which the sample came. And so we're instead just trying to say, okay, like the correlation between the output and the specific sample we use to obtain that output should not be too great. There's one way perfect generalization. And this is kind of similar. And again, we're trying to say that the particular sample we used is not going to be revealed, or like we're not going to learn too much about it from the output of the algorithm. So in particular, here we're imagining that there's some distribution that will be induced by the target distribution we're trying to learn over. Right? So it'll be a distribution, say, over like good outputs of the algorithm A. And it should be the case that if we look at the distribution of outputs of A, once we've fixed the sample, but we're allowed to re-randomize the randomness of A, that distribution should be sort of close to this idealized distribution that of outputs that we imagine that we're getting from, if it helps to sort of ground you, you can imagine it being the distribution over all runs of A, where both the sample and the randomness are re-randomized. So that's sort of we're saying once we fix the sample, we're not changing the distribution too much from this idea. And so this is introduced by Cummings, Leggett, Nissim, Roth, Wu, and also Basilian Find. I already talked about replicability. So any questions about these definitions? So why do we care about connecting them other than, let's draw nice diagrams, and we do love drawing nice diagrams. Like what, what's going to motivate us wanting connections between these various notions? And so here I want to talk about one of our applications. I'll go back for a second. So what this diagram lets us do, amongst many things, is if we start here at differential privacy, we can convert to an algorithm with bounded max information, convert to a one-way generalizing or perfect generalizing algorithm, convert back or convert to a replicable algorithm, and then obtain a differentially private algorithm, right? So we can convert differential privacy to differential privacy, which may sound like a joke, but is actually useful in the following instance, and that's privacy amplification. Yes. So yeah, these ends here are for the sample complexity of the algorithm that's being transformed. So some of these arrows are going to follow by explicit transformations, some are going to follow definitionally. And so there will be a sample complexity blow up for some of these arrows. But notably, like if you walk this whole circle, you'll get a blow up that's like n squared over epsilon log.
The top arrow, I assume it's only if you do not release the randomness.
So what we're imagining, what we're going to do here is show that essentially you can, so I think what you're saying is true, and that we're going to take a replicable algorithm, we're going to run it a whole bunch of times, partly to ourselves. So yeah, we're not going to release randomness, but we're going to use the fact that there are sort of canonical representatives for a given output string to give us privacy.
I think just to be clear, we're saying there exists an algorithm with one property implies there exists an algorithm, not necessarily that the same algorithm is going to have the property.
Okay, so going back to why we would ever want to convert privacy to privacy. So if we start with an epsilon delta differentially private algorithm, generally what we'll want in particular, we want all of these parameters to be small, but in particular, we want the delta parameter to be very, very small, right? Because if delta is large, then seeing a particular output can be very informative about the sample. And so we'd like this delta to be very small. In particular, we'd sort of like it to be like, like inverse exponential in the sample size. But what if we start with something that says it has like a polynomial relationship instead? There are privacy amplification techniques that rely on taking a larger sample and then subsampling. So here, if we just took a larger data set in both cases, If we subsampled, then like maybe we don't even end up subsampling Marco at all. And then when we look at the two runs of our algorithm, they'll be exactly the same because we actually looked at the same data set. So we can take a larger data set, subsample from it, and improve our privacy parameters. But this actually isn't going to be enough to get us from the regime, if we're in this polynomial regime, to this exponential regime dependence that we'd really like. So our tracing through our diagram actually allows you to obtain privacy amplification for delta to get to sort of the target parameters we'd really like. So amongst other applications, we can also use like all of the work that's been done for differential private algorithms and apply that to replicability, right? So replicability sort of seems like this very strong ask from an algorithm, and that we want exactly the same output, not just sort of close distributions. But then we can say, okay, well, we already know how to do tons of things privately, and then we can trace through our diagram. We can now do them replicably. In particular, we can get replicable pack learning for finite hypothesis classes. So this will follow from results of Viswanathan, Lee, Nissim, Raskolnikova, and Smith, which showed how to obtain epsilon 0 differentially private alpha accurate agnostic learners for any sort of finite hypothesis class with this logarithmic dependence on the size of the hypothesis class. You get our transformation, and you get this quadratic blowup, but we now have like sample efficient replicable learning. I should note that we can actually improve this dependence on alpha in a realizable case by a direct proof, but it's still cool that we can get this just by walking a diagram. So now that we know why we care, or some of the reasons we might care about transformations, let's actually draw some of these arrows. And because some of these transformations might be efficient, some won't actually entail a transformation at all, and some are inefficient, I'm introducing the following star system to denote which ones are efficient and which ones are inefficient. The idea being a star means you're efficient, and then the most efficient way to become a thing is to already be that thing, and so you get 2 stars if no transformation is required. So to show that replicability implies both one-way perfect generalization and differential privacy, I don't want to go into this transformation too much because I want to be able to talk a little bit about the ones I think are a bit more interesting. But I will at least observe that both of them have, like modest blowups in the sample complexity size. And the idea in both cases is going to be sort of the same. So I can maybe give you an idea if you're curious about how we're going to convert from replicability to this generalization notion or differential privacy notion. The idea is we're going to start by populating a row of a table here by picking a random string. Okay. And then we're going to pick a whole bunch of samples from our distribution, run our replicable algorithm on the string we chose for this row and all of the different samples. If the particular string we chose was good for replicability, which it will be with good probability, then there should be some output in this row here that is, there should be like a majority output, or there should be a very frequent output. Okay. And so on for each of the rows. Maybe some strings will be bad and there won't be any clear majority, but it should be the case that for most of the rows, there's a majority output. And in both of these transformations, what we're going to do is preferentially output the results that we see with highest frequency. So what exactly that means will differ in both transformations, but that's sort of the idea. So to get from epsilon differential privacy to epsilon delta max information, most of the work, or some of the work was already done for us in this work of Roger Schwarzsmith's Dacker. And they show that epsilon delta differential privacy actually just implies max information for particular setting of parameters. Okay, so if we're epsilon delta differentially private, then that same algorithm will have this max information these max information parameters, which is a little bit annoying because they have these like M terms that maybe we don't like, right? Like maybe we want something tighter that's not actually going to depend on the sample complexity of the algorithm that we started with. But then we can use this sort of subsampling procedure that we just talked about. Right, so we know that if we just take a large enough sample, particularly if we take, we blow up our sample by another factor M, that we can perform the subsampling and then get the epsilon delta differential privacy parameters compared to the sample complexity that allow us to get max information parameters. In particular, we can end up with something. We can end up with like epsilon max information so long as we started with a small enough delta. But again, like it's typically delta is going to be very, very small in terms of the sample complexity. And so this is a very modest assumption. This isn't a particularly strong. Cool. So that's how we're getting from privacy to max information. And again, this is just this is a 2-star transformation, so it's not actually a transformation, just follows definition. Now to hop from max information to one-way perfect generalization, we have something else that just follows definitionally, right? So these two definitions were sort of similar in the first place, right? We're saying, okay, we want to say that the sample, or I guess the output of an algorithm run on a particular sample is not too informative about the sample that we use. And so by picking our ideal distribution that we're comparing to be this definition that this distribution I talked about before, we can show that this follows definitionally, right? So again, we're going to imagine SIMD in the definition of perfect generalization to be the distribution over outputs of A, given samples from the target distribution D and uniform randomness. And then again, if the output of A is not too informative about the sample, then it's going to follow that we're also perfect. So these parameters, again, are just want to be a little bit clear about how they're transforming. So if we started with epsilon delta max information, then we're going to get root delta to epsilon root delta one-way perfect generalization. Great. And now we come to the problem child of our diagram. You'll notice there are no stars on this arrow. So this is the transformation from one-way perfect generalization to replicability. And there is a construction that allows us to transform from one to the other, but it is not always going to be efficient. In fact, I think like the best procedures we have for this one only work for finite range and are exponential. And so we don't necessarily, we necessarily don't have, if public cryptography exists, efficient transformations from one-way perfect generalization to replicability. This connection, however, the statistical connection utilizes a technique called correlated sampling. And I want to talk a little bit about that so you can see like where the bottleneck is coming in. So what is a correlated sampler? A correlated sampler is some algorithm that's going to take a representation of a distribution that we want to sample from. Here we'll call that QD. And in particular, we're going to require that it has finite support. Okay, so this is going to throw that finite support restriction into our diagram. And so we're only going to be able to go the way around if the output of A is finite. Okay. And we'll let R denote some random string. And a correlated sampler is going to take in its representation of a distribution and the random string, and it will output something in the support of the distribution it should be sampling from. And it should be the case, if we're actually a good correlated sampler, that we are in fact sampling from the target distribution, right? So we output an element Y with the same probability it appears in D. And then the correlated part is coming from the fact that if we fix the randomness between two runs of our correlated sampler on two different distributions as input, right? So we're going to get the two different representations of two different distributions, fix the randomness. We should still get exactly the same element out of our correlated sampler, except with probability that's proportional to the total variation distance between those two distributions. Okay, so if we're given exactly the same distribution or something that's very, very close in total variation distance, then with high probability, we should get the same element out of our correlated sampler.
And D prime has the same support.
Yes. Yeah, so because it's finite, we can just like take the union of both of them and say, okay, no, that was really your support all along.
So the assumption is that the correlated sampler takes the representation in R and outputs with the sampler.
When you say a finite range, you mean like a constant size or just finite? Like, in a general sense?
Just finite, or I guess like, what do you mean? Maybe,
Like,
it could be any kind. We don't need to like be below some particular.
Okay, okay.
Yeah, just fine.
The constant is
size.
No. Yeah, I mean, like, it's really, I'm not actually going to talk about like how to instantiate correlated samplers. So this is just sort of like definitionally, we just want it to be about that. Yeah. We'll be happy calling you a correlated sampler if you can give us any constant on that. Cool. All right, so what are we going to use this correlated sampler for? So we can imagine, right, I guess in this setup of replicability, we want to take two samples from the same distribution and get the same output, right? And so we can imagine, all right, here's our algorithm on some sample S, here's our algorithm on some sample S prime, and we get some distribution over outputs in either case. And if we use our correlated sampler to sample from the outputs of either of these distributions, where again, the distribution is fixing S and then randomizing the internal randomness of A, we'll get some sort of output, right? And what we want to say is that, okay, our correlated sampler is going to give us exactly the same output. So we want to be able to say something about these two distributions, right? We want to be able to say, oh, they're actually close in total variation distance. So our correlated sampler is actually going to give us exactly the same output, and then we'll be replicable. Okay. And that's what this one-way perfect generalization allows us to say, right? So we're going to say, okay, well, there is this distribution sim D that we were close to, regardless of the sample that we fixed, right? So we fix sample, we get something that's close to this idealized distribution. And because they're both close, they must be close to each other. And so our correlated sampler will give us the same output with high probability. Great. So again, this is like the biggest issue here is implementing correlated sampling. Right? So again, we're going to need to restrict ourselves to algorithms with finite domain, and then we're going to need some sort of efficient way of carrying out this procedure. Cool. So you might ask, is this just, are we just bad at our jobs, right? Like, can we just like not come up with a good correlated sampler? Did we not try hard enough? Is there in fact some way that we can make every step of this diagram computationally efficient? And the answer is no. We did try, and assuming public key cryptography, or I should say like under some standard public key cryptographic assumptions, we're able to show that there are problems that you can solve efficiently with differential privacy that you cannot solve efficiently using replicability. You would break public key cryptography. So there are sort of general assumptions, and then you can instantiate them with like GGM if you like. We essentially need re-randomizability. The idea here is we're going to have some sort of promise problem where you have like a distribution over encryptions of 0, distributions over encryptions of 1. And the problem is to output an encryption of like the majority bit that's encrypted from your sample. You can do this privately if you have a re-randomizable encryption scheme, because I can just pick one at random, re-randomize it, and output that. But if I could do this replicably, then that means there must be some canonical encryption of the majority bit, and canonical encryptions are generally bad for in CPA security. So yeah, so it's just re-randomizability, and then this. Well, okay, so right, under standard public key cryptographic assumptions, there will be an inefficient step in this diagram. On the other hand, if one-way functions don't exist, there actually always exists an efficient correlated sampler. So we give a construction for, okay, if you can just invert all of the functions, you can do this correlated sampling efficiently. But there is a sort of gap in these assumptions, right? So we don't really know, okay, is it mini crypt or crypto? So that's sort of the map of these relationships between stability notions. And again, like here is the expected sample complexities of each step. And so again, you see that going from the differential quadratic log 1 over delta over epsilon blow up in terms. So this is very efficient, except for computational efficiency. And cool, that's all I wanted to talk about for these connections. I do want to say a couple of words about future and ongoing work. So this is a question of, okay, like what about correlated sampling for infinite domains, right? Everything I've talked about so far, we only know how to do for finite domains, but it'd be great if we could say something for infinite. And also going back to original motivation, right, which was fixing science. It would be really great if we could do practical replicable hypothesis testing, right? So we're sort of getting part of the way there with our replicable statistical queries. But because of the sample complexity lower bound, we're kind of asking, in this case, scientists to like collect way more data than they were previously. And that can be an issue in practice. And so if there's some sort of is there some sort of setting or some particular formulation of this problem where we can get around our lower bound? I'm also interested in applications to reinforcement learning. In particular, I'm looking at this with Marcel Hissing at UPenn. So if we want to adapt this replicability setting to reinforcement learning, we can imagine samples rather than coming IID from sort of distribution we're trying to learn on. We can imagine our samples as being the state that we move to when we are in some state and take some action. And we will want to be replicable in the sense that if we got different transitions, if we ended up in different states after making the same choices, that we should still be able to converge on exactly the same policy after some, like polynomial number of steps. Also interested in exploring relaxations of our definition for other settings, right? I mean, we have this very strong ask of equivalence of the output, and we are able to show all these connections to other like very reasonable notions of stability. But we might also ask, like, what if we don't care about like syntactic equivalence, right? What if we care about functional equivalence? So I'm interested in looking at relaxations of this definition. We want to obtain algorithms that output models that make these same decisions on, like, say, all but an epsilon fraction of their inputs. So that's all I have to talk to you about today. I'm happy to take any questions either now or during lunch.
Thanks for questions. I have a very basic question. It's just about this notion of replicability learning. So do we have like examples of the separation, computational separation between like a factor and class efficiently, but perhaps not with this replicability? Is it possible?
So I guess you could say like through privacy, right? There are like, I mean, so I can imagine like, yeah, more spaces, but yeah, yeah, that's, yeah, I guess like through connections to privacy, you pretty much just like inherit the connections that affect on the data.
Even though your connections are not how efficient, you say you can still recover. Right.
Yeah, okay, so I guess you're meaning like actual constructive
just a natural class that I can efficiently factor, but perhaps I cannot factor with replicability. I just understand.
Yeah, so I guess again, this sort of thing, like things from privacy. So we have a lot of lower bounds for like thresholds, I guess, that are going to depend on the size of the domain, for instance.
More question?
sorry, in the application of like a science, when is the idea, so like you do an experiment using one of these mechanisms to like produce your statistics and release the coins. The idea is that someone does the same experiment on the same coins would be able to identify that their data is different, or like I guess what I'm trying to understand, like what is the confidence someone gets from like reproducing an experiment using this mechanism, like I don't know if this makes any sense.
Oh, I think, okay, so I guess maybe there are a couple of questions that you could be asking, and maybe one I'll say is like one of the benefits potentially to using a replicable algorithm for data analysis is, I guess, sort of like narrowing the attack surface of failures of replicability in a sense. So I can know that if I failed to replicate for some reason, it's not because there was a statistical fluke in my sample. So in some sense, it's like, in one sense, it's both like assisting replication efforts and saying, okay, as long as you publish the randomness, you should get the same with the replicability. But it's also,
Like identifying the,
yeah, it's sort of saying, okay, like look elsewhere for failures of replication.
Yeah, if not, let's thank Cascade.
So yeah, something completely different.